Hey guys, so here are your notes on plate tectonics. So on our first slide, we see that we're calling this the unifying theory. So this is a scientific theory, which means it has been tested many times. We don't have a better explanation for all of the observations that we are making. In this case, the observations are mountain ranges, volcanoes, earthquakes, trenches, um, underwater volcanoes, volcanoes on land. All of those things can be explained by plate tectonics. So a little bit of our history of plate tectonics. So in 1910, an American, his last name is Taylor, he proposed the idea of continental drift, or that the continents are actually moving. He didn't have any evidence, however, so no one believed him. Then 5 years later, Alfred Wegener, who was from Germany, he proposed the idea of continental drift in a book, and he also had the idea of a supercontinent called Pangaea, where all of the continents were originally one big land mass. And about 45 years later, continental drift was finally accepted. So it took a little bit of time for people to accept this idea. And again, this is kind of a picture, multiple pictures of how Pangaea broke up over time to give us our continents where we see them currently today. So at the time, there was evidence that the continents were moving. So we have a few pieces of evidence for that. The first is our fossil evidence. So we could see that there were fossils being found on continents that are far apart now. And we can see from these colored bands on these continents here that if those continents were once together, it would make sense that these fossils would be found in these kind of bands. So especially like some of these fossils that span multiple continents, that gives us evidence that those continents were once together. We also have what we call biogeographical evidence. So this is not necessarily fossils. We're talking about modern animals that live today, and how they have similar ancestries, even though they're found very far away from one another. So for example, we see these different birds that have similar ancestries, even though, again, they are far apart. But if those continents were closer together, like we believe that they were, it would make sense that they would be similar. Another piece of evidence that our continents are moving is our rock structures. So there's kind of two parts to that. There's the fact that they just genuinely appear to fit together, kind of like the pieces of a puzzle. And then secondly, because of the types and ages of the rocks that are found on our different continents. So for example, the rocks that we have in the Appalachian Mountains here in North America are similar in structure as well as age to the rocks that are found in the British Isles, which are in Scandinavia. So we are talking about here we go. So here are the Scandinavian mountains here in very northern Europe. And so those are similar to the mountains that we have all the way over here in North America. So again, the idea is that they may have been, or they were, close together at one time. Another piece of evidence for continental drift is looking at evidence of ancient climates. So in this case, we're looking at evidence of glaciers. So places where we don't necessarily have glaciers now, but we did at one time because those continents were in colder climates, or closer to the poles. So we could see that with glacial grooves and glacial till. And so again, if all of those continents were closer together, and we can see from the evidence like that those glaciers were moving away from the South Pole, that they would have once been together in a picture sort of like this one. So glacial grooves, we actually have those close to us here in Ohio. We have them up at Kelly's Island in Lake Erie. So here are some pictures of the glacial grooves at Kelly's Island that I got to see a couple of years ago. So again, we don't have glaciers there now, but at one time there were glaciers in this area and or closer to the poles. Okay, so even though we had evidence that the continents were moving, the scientific community still didn't really accept continental drift from Wegener because he couldn't provide a reason why they were moving. So when we say a mechanism, we're saying like, how were they moving? So since he didn't have that, people didn't really believe him. And over time, as we've gotten more data and more technology, we've been able to provide a mechanism for why those continents are moving and the different ways in which they can move. So just like we do in science, we get more data, we get more technology, we get more people thinking about it, and then that changes things. It changes our understanding of whatever we're trying to better understand. So what we've learned is that the reason our continents are moving is because our continents are on what we call plates. So the theory of plate tectonics says that the lithosphere of the Earth, okay, so our lithosphere is made of, as we see this little bracket here, it's made of crust. So it could be continental crust, that means just crust that makes up land, or it could be oceanic crust, that's the crust that we find at the bottom of our oceans. So it includes the crust and it includes the uppermost part of the mantle. So hopefully we're recalling from our previous science classes that we've got the crust at the top, then the mantle, and then our core in the center. So those are still important words for this class, but we're just getting into more detail with those layers. So the lithosphere includes the crust and the uppermost part of the mantle. It is floating on a semi-liquid layer, which is here with this little bracket called the asthenosphere. You can see it's being described here as plastic or a semi-liquid layer. And that is above the mesosphere, which we see here. So all of these parts, so the uppermost part of the mantle that's in the lithosphere, the asthenosphere, and the mesosphere all make up the mantle. So we've learned it maybe in other classes as just the mantle to make it easier, but it's really made up of even more specific layers. So our lithosphere is floating on top of our asthenosphere, which is still pretty high up in the mantle. So that lithosphere, so the crust and the uppermost part of the mantle, is divided into these big pieces, which we call plates. And you can see from our image here that some of our plates are big. And like the North American plate, that's a huge plate, or the Pacific plate, for example, or the Eurasian plate that actually wraps around this map. But then we also have some smaller plates like the Caribbean plate, for example, or the Scotia plate here. So lots of different types of plates, lots of different shapes. And then they move and they continue to change their location and their shape, and they are going to be moving at different rates. So you can see some of them move up to 2 inches per year, which is kind of a lot when you think about how far they can move in, just 100 years. So how are the plates moving? Well, so in that mantle that we discussed, there's an unequal distribution of heat. So it's not all the same amount of heat in every location. So the areas where it's hotter will cause the mantle to move upward, and then it will cool, and then it will sink, and then it will heat, and it will rise, and it will cool, and it will sink. And we've learned about this before in physical science. We learned that that was called convection. So we're still calling that convection here, except before when we talked about convection, maybe we were talking about like boiling water, or maybe we were talking about air being warm and rising and then cooling and sinking. But in this case, we're talking about this happening in our mantle within the magma of our Earth. So as that happens, as the magma is cooling and moving outward, it's kind of dragging the plates that are on top of it with it. And that causes them to spread apart, which causes in other areas for plates to come together. So, in speaking of bringing the plates apart, we have what we call divergent boundaries. These are also called constructive margins. So as the plates move apart, we're not just going to be left with an empty gap. There's going to be mantle or magma underneath that's going to come up in the middle. And so that's going to create some new crust. That's why we call them constructive margins. We're making new crust, new land, ultimately. So when this occurs, this creates what we call our ridge systems. So these are called oceanic ridges. They're also called mid-ocean ridges. And that's what is responsible for what we call seafloor spreading. So usually in the middle of our ocean, we've got new crust being made and our old crust is being pushed out. So again, this can vary depending on where you are. So like in the North Atlantic Ocean, this happens at about 2 centimeters per year. But in the East Pacific Rise, it happens at 15 centimeters per year. That's a huge difference. So looking at our ridges, so North America, this would be our mid-Atlantic ridge. It's in the middle of the Atlantic Ocean, go figure. And then our East Pacific Rise, we can see, is here to the west of South America. So this is spreading at a faster rate than here in the northern mid-Atlantic ridge. And we can see some other ridges as well, some being kind of in the center of oceans, some not so much. So those are our oceanic ridges. So here's just a picture of what's happening here. So our hottest magma is rising here in the center, and as it moves out to either side, it's pulling that crust that's along the top with it, and it causes it to spread out. And so in the middle, we get a ridge. Okay, and at this ridge, we've got magma coming up, so we're going to have some volcanoes here. We can have some earthquakes here from the shifting plates. And again, new crust rising up in the middle. So divergent boundaries can also be formed by what we call continental rift systems. So in this case, basically what's happening is we've got a hot spot, which we'll talk about in more detail in a few more slides. But basically, we've got a plate over a hot spot, over a particularly hot part of the mantle. That extra heat causes that crust to expand and form a dome, and then it reaches like so much, it's being stretched so much that it breaks or it will fault. And so that will break that larger plate into 3 smaller plates. And so normally it has 3 arms, or it will spread in 3 directions. So in this case, we've got the East African Rift Valley, we've got the hot spot in the middle, and we've got 3 arms or 3 directions where this larger plate has kind of broken into pieces. And so this is where we're going to get some divergent boundaries forming over the next couple million years. In convergent boundaries, our plates are going to come together. And so it depends on what type of crust we have coming together to determine what will happen. So first of all of these are considered destructive because we're going to be destroying crust instead of creating new crust. So if those two plates are both made out of continental crust, so like land, neither one of them will subduct under the other. So they're both going to push upward, and that's going to cause mountain ranges to result. If they are both carrying oceanic crust, so oceanic crust is more dense, whichever one is more dense out of those two pieces of oceanic crust will subduct under the other, and that's going to cause a trench to form, underwater volcanoes, and or those underwater volcanoes might become large enough that they come above the water surface, and now they're called volcanic island arcs, or just volcanoes that have created an island. So these are going to be volcanoes that we find in water. Our other option is if one plate has continental crust and the other one has oceanic. The oceanic one is going to be more dense, like we said, and so it will definitely subduct under the land. When it subducts, it's going to get hotter because it's going to go deeper into the earth, and it will melt. It will melt enough to be hot enough to then rise, and when it rises, it can form a volcano on the land or on that continental plate. So we've got lots of possible things happening here: mountain ranges, volcanoes either on land or in the water, trenches, and then any of these situations can also lead us to our earthquakes, which we'll be covering in more detail in our next unit. So our pictures then, so here we've got our continental crust with another piece of continental crust. They're pushing up, they're making our mountain range. And here I've got out here in the ocean, I've got my oceanic crust and my oceanic crust coming together. One is subducting under the other. Subducting under the other, it gets hotter because it's deeper in the earth. So now it has, it's less dense and it's hotter, so it's going to rise and it can form an underwater volcano, which maybe will peak above the water surface and create what we call a volcanic island arc. And then this area here where those plates have collided and made this deep area, we call that a trench. So that'll be found somewhat close to our volcanoes. And then finally, if I have oceanic crust subducting under continental crust, again, whatever subducts is going deeper into the earth, getting hotter. So now it's able to rise, and in this case, we're getting a volcanic arc that's not an island arc because it's not in the water. So we also call these continental volcanoes or a continental volcanic arc. We'll still get a trench here from where those plates collided, and we have the deepest area there. Transform boundaries are not going to make new crust. They're not going to destroy crust. They are what we call conservative margins because we still have some movement, but we're not creating or destroying crust. So our transform boundaries are gonna, instead of moving toward one another or away from one another, they're kind of doing like this, like sliding past one another in this kind of way. And that can also create earthquakes for us, but not like our volcanoes or our mountains like we saw in our other types of plate boundaries. So again, that movement of moving past one another instead of toward or away from one another. And I think that's where I'll stop for this video.